Okay, so yeah, we are studying a least squares problem, which is a more flexible version of linear systems. So even though our vector b is not inside of the column space of an A, so previously we concluded that we have no solution, or no solution exists, but now we can solve it approximately, right? By having, let's see, yeah, this kind of minimization, yeah, by changing the linear system into this minimization problem. And then the main point of what we learned last time was the solution for this minimization problem is the same as, let's see, so you guys remember the normal equation that we learned last time. That normal equation is composed of like a zero inner product equation. So multiple equations where each is composed of this residual vector commonly, and then each column, right? Yeah, so each column in A as row now, and so that way we can specify that our residual vector from B to B hat, which is in the column space of an A. So if B hat is the closest possible approximation of B, and then the distance between B and B hat has to be minimized, and then also that vector should be orthogonal to any vector in the column space of an A. So the first column and the second column and so on. So that way we obtain this A transpose minus times B minus AX. So this guy is B hat, right? Because B hat is now in the column space of an A. So it can be represented as A times X with some linear combination coefficient as this X vector X. Okay, then this guy. Finally, we have this very famous equation called a normal equation, which is A transpose A times X equals A transpose B. And then, yeah, from from the minimization problem of like this problem, we now obtain this linear system. Okay, and then the solutions between these two different problems, where the first one is minimization problem and then the other is just a linear system, the solution set are exactly the same between them. And also in this equation, as we saw in some example last time, A transpose A will come out as, will be always a square matrix. It's not like a tall and thin matrix or short and fat matrix. Our new A matrix in the linear system, that matrix will always be the square matrix. Okay, and then now, yeah, let's quickly go through this theorem 14. So again, we will not prove it. The proof, the detailed proof is in the exercise problem in this chapter. But I'll give you just a conceptual or intuitive understanding about how we understand this theorem. So this theorem is saying we have this least square problem. So we have to solve AX minus B, and we have to minimize the difference between AX minus B, and this guy was actually B hat, right? Okay, this minimization problem is the same as the solution. Yeah, it has the same solution set as this normal equation, right? So I'm just reiterating this very much important fact. And then if the solution for this minimization problem is unique, which means our B hat, which is a orthogonal projection, that point is represented as a unique linear combination of the columns of an A. So that way, this x will be obtained as a unique vector, right? And so, if this minimization problem has a unique solution, and then it means that projection vector will be represented as a unique linear combination, or will have a unique solution, and then it means the basis vector or the columns of an A are linearly independent, right? So I explained it last time, right? So from B, we do the orthogonal projection, and that point will be B hat, right? And then that now we just forget about the original B. We only consider this B hat. So B hat is always determined unique, as a unique. And then we have to find out the linear combination coefficient to represent this B hat using the columns of an A. Okay? And then if the columns are linearly dependent, and then in order to represent this unique point of B hat is unique. It's always true. Right? Because orthogonal projection, we cannot think about the different orthogonal projection. We will always have a unique orthogonal projection. And then now the problem is we have to find out the linear combination coefficient using our columns of an A that spans our subspace. And so if the columns are linearly independent, and then we can uniquely represent this point as a one unique linear combination. And then that's when this minimization or this least square problem has a unique solution. Okay? And then if the columns of an A are linearly dependent, which means they are redundant with each other. So in this case, in this two-dimensional hyperplane, we have a three vectors that spans these plane. And then in order to represent this point, we can have a many different linear combination representation, right? That's when we have a infinitely many solution, right? Okay, and then now let's look at those two cases of a unique solution and an infinitely many solution from the perspective of this normal equation. This normal equation is this guy, just a square matrix, right? A transpose A is just a square matrix, and we have an X here, and then this guy is also another vector. So this is known, and this is also known, right? This is just a typical linear system. Then now, when is this linear system having a unique solution? When does this have a unique solution? It's when this part is invariable, which means if our matrix is a square matrix, invariable is the same as they have a linearly independent columns, right? And then also each row has a pivot, right? So all these many items that we saw in the invariable matrix theorem, right? So you guys remember that, right? And so that should be invariable if the solution for this linear system is unique, okay? And so we can kind of kind of make some interesting conclusion that from here in the least square problem, if the columns of an A are linearly independent, and then we will have a unique solution, right? And then in this case, what was this guy? This guy is A transpose A. So if the columns of an A are linearly independent, and then A transpose A are invariable. Okay? So that's from our intuitive understanding that the solution set between these two should be the same. Okay. So, theorem 14 is saying that all these three are equivalent. So this is describing the case or the situation where we have a unique solution for the least square problem. Right? So the first item is saying the equation ax equals b has a unique least square solution for any b, for each b. And then the item b is saying the columns of A should be linearly independent. And then the last item or the third item is saying that our matrix A transpose A is invariable. Okay, so this is exactly what I just described. Okay, and then in case it's an in case this guy A transpose A is invariable, or equivalently if the columns of an A are linearly independent, and then what will be our solution? It will be just simply the solution from this normal equation, right? So A transpose A, X equals A transpose B, and so because this part is invariable, so we can just simply compute its inverse times the new B part, which came from here. Okay, so this will be your least square solution. And yeah, so let me discuss maybe a bit different situation, which is not discussed in this theorem. So what if the columns of an A are linearly dependent? And then in that case, we will have a infinitely many solutions. So again, from our intuition or from the process of doing of this orthogonal projection, orthogonal projection is always determined as a unique point, right? And as I mentioned last time, it is So is there any case that we cannot perform orthogonal projection? So we are given some subspace and some B, which is possibly outside of our subspace, and then we can always do orthogonal projection, right? So what I mean, I mean that. So I'm trying to emphasize that orthogonal projection can be always done. It's always possible, right? Given a subspace, even when it's the smallest one of the 0 point, we can 0 point. So we kind of ignore that because zero subspace. What is the basis of a zero subspace?
Just the zero.
So that was the last question of the previous exam. So right. So let's see. Okay, your subspace is in three-dimensional space, but it contains only 0. And in this case, what is the basis of subspace S? Is it 0 or what?
Just 0.
Just 0. It could be natural to think that way, but the answer is empty set. Why? The basis, by definition, it should be linearly independent, right? And zero vector itself is not linearly independent already, even with just only one vector, because 0, 0, 0, and then we are thinking about the homogeneous linear system, right? And so we can have like a many non-trivial solutions. Wow. So it should be 0. Nothing, empty set. Empty set. Okay, so in our subspace, because the basis is an empty set, so we kind of exclude that 0 subspace. Okay, so in whatever subspace, we can perform always like an orthogonal projection. Okay, and so after doing that, after obtaining that orthogonal projection, which is now inside of our, which we can guarantee that is inside in our subspace, right? It's inside of our column space of an A, so we can guarantee that the solution is always exist when for this least square problem. So least square problem will always have a solution. It cannot have no solution. Okay. Okay, so that means this normal equation should always have a solution. Should always have a solution. And then also from the perspective of this normal equation, if A transpose A is not invertible, so they are not invertible, which means their columns are linearly dependent, and then their the span of the columns will not fully span, for example, R3. If A was 3 by 3, it will not the columns will not fully span the entire three-dimensional space, right? And then what if this vector, which is our A transpose B, is outside of the column space of this matrix? In that case, this linear system may not have a solution, right? Right? But the fact that the least square problem should always at least have one solution. This linear system should always have at least one solution, which means this guy is always inside of our column space of this matrix, even when they are linearly dependent. Okay, so I'm not gonna prove it, but yeah, this is something that you can think about, like why this guy should always be like a column space of our new matrix of A transpose A. Yeah, so yeah, this is a little bit of an outside of this theorem 14, but this is something that you can think about. But anyways, that is this theorem 14. And then let's think about some special case where our matrix A has some orthogonal columns. Orthogonal columns. Then what would be our B hat? So previously, if A was not orthonormal or orthogonal columns, A was just this kind of matrix, which is not orthogonal. They have some angles, not 90 degrees, right? In that case, all we wanted to find was this B hat, which is AX, and we wanted to find this orthogonal projection B hat, and then we want to find the linear combination coefficient of X, right? So B minus AX, which is our B hat, so that should be minimized. This is the least square problem, right? So here, did we explicitly obtain B hat? We didn't, because we just replaced B hat by AX and then constructed the normal equation like B minus AX, and then A transpose, which has the rows of an A, the rows as the columns of an A, which is A transpose, right? So that's how we constructed the normal equation, and then that's how we solved this X. But now, in case A has a orthogonal columns, so let's think about this special case where the columns of an A are orthogonal to each other. In that case, we can easily compute B hat from what we learned in the previous chapters. That's when the matrix is orthonormal, has orthonormal columns. Yeah. So yeah, in the case of kind of general orthogonal projection formula, this was our orthogonal projection formula, right? So we are given the two vectors that are orthogonal to each other, and then the orthogonal projection to that subspace spanned by these two vector a1 and a2, and then that's computed by this simple formula, right? This is a b hat. And then now what will be our, so suppose that was computed as this representation, which means this guy, the linear combination coefficient attached or associated with the a1 is 2, which is 8 over 4, and then this part, which is our linear combination coefficient, is this guy, which is 1 over 2. And the orthogonal projection b hat is represented as a 2 times a1 and 1 over 2 times a2, right? And then what was our goal in the least squares? We want to solve, let's see, this x, which is a linear combination coefficient for our orthogonal projection b hat, or approximated version of b hat, right? And so this b hat is our approximated version of b hat, the best approximation, right? And that best approximation is represented as a linear combination in terms of columns of an A, right? So the solution x will be just 2 and 1 over 2, because we already obtained these linear combination coefficients from this orthogonal projection formula. So does it make sense? So we didn't even need to construct any kind of normal equation. Okay, so we can just simply obtain the least square solution very easily by just doing this orthogonal projection. But this is only possible, or this is only true when your matrix A is has orthogonal columns, right? And then let's see. And then let's try to construct our normal equations anyways. Okay, so A had these two columns which are orthogonal to each other, and then in that case, let's just try to construct this normal equation. And what will be that? What will be this A transpose A? A transpose A. Okay, so let's simplify the case. So these two columns are orthonormal. So let's call that as U1 and U2. So these are orthonormal columns. They are having the length of 1 and then having a 90 degrees. And then, so let's call this as Q. And then in this place, it will be Q transpose Q. What will be that matrix? 1, yeah. More exactly, 2 ones and zeros for, yeah, identity matrix, right? And so if you construct this a normal equation, yeah, in case your matrix is having also normal columns, and A transpose A will become identity matrix. So this guy can be just easily removed or cancelled, removed as an identity matrix. And then your solution will be simply this guy. And then what about this orthogonal case? So not yet orthonormal, but just orthogonal. 90 degrees, but they are not yet having the length of 1.
Elementary matrix E and in the form of like some row operated from identity matrix.
Yeah. So yeah, you're almost right. So in this case, A transpose A. First of all, this matrix will still be diagonal matrix, right? And then what will be these guys? these guys are
non-zero number.
the lengths of the vector of this A1 and A2, right? The squared lengths, right? So the lengths, squared lengths was 5 and 3, and this will become 5 and 3, right? And then you will obtain this A transpose B as just some vector, right? And then this guy is just nothing but the inner product between A1 transpose and our B, and then A2 transpose and our B, right? That's how we obtain these two entries, right? And then if your matrix is diagonal in this linear system, and then you can just simply divide this guy by 5 and divide this guy by 3, right?
Do the same row operators to both of them.
Yeah, but you don't even need to do any kind of complicated row reduction or row operation. It's just simply like if you just reduce, if you just convert it to just the equation form, and then this guy is like a 5x1. So let's set these values as 1 and 2, for example. And then 5x1 is 1 and 3x2 equals 2, right? So that way you can
by division.
Yeah, just the division element-wise, in an element-wise manner. And then this is actually the same as this guy, orthogonal projection. Let's see why. These guys, BA1, B inner product with A1 and BA2, that is these two. Right? So these are the numerator part. And then what is the denominator in this orthogonal projection? Denominator was square the length of each vector, which are orthogonal bases, right? And then they are coming from here, right? So so here we can see one interesting fact, or one interesting property, that if your matrix A has orthogonal columns, all orthogonal to each other, and then or orthonormal, which is a even simpler case. In these cases, this normal equation is really easy to solve because they are just a diagonal matrix or even simpler form of identity matrix. Right. So the last theorem, which is theorem 15, is about this orthogonalization. So if your matrix A, the columns of an A was not originally orthogonal to each other, so like this kind of basis matrix or columns, they are not orthogonal to each other. But we learned the way to orthogonalize these three columns, right? That was QR factorization. So the first vector, and then we normalize it, and then for the second vector, and then we project it, and then subtract that projection part, which is explained part by the previous subspace or previous vector, and then the remaining vector will be like this perpendicular vector or orthogonal vector, and then normalize it. And that's how we obtain the second orthogonal basis vector that will span the same subspace spanned by the first two columns, right? So this orthogonalization of the matrix A, which is our QR decomposition, is actually giving us an easier way to solve this normal equation, and this is how we can easily solve it. So suppose you are given, let's see, suppose you are given this least square again. Okay, then now the situation is someone already gave you the QR decomposition of your matrix A. But here, in order to obtain the QR decomposition, you have to have an assumption. So we need the assumption that the columns of an A should be linearly independent, right? So the initial assumption of QR decomposition was the columns of an A are linearly independent. In that case, like if those two vectors are orthogonal, they are linearly dependent, and then after constructing the first basis vector, the second one will be completely explained by the first one. So it will have just a zero residual vector. So we cannot obtain any additional basis vector, right? So that's why we excluded linearly dependent case. Okay, so we obtain, suppose we already obtained the QR decomposition of an A. Okay, and there are several different ways, but let's think about this normal equation. Again, we are seeing this normal equation. And then, let's see. Let's compute this A transpose A. And then A transpose A will be R transpose, Q transpose, Q, and R, right? And then X, and then Q, R, B, right? So first we get, right? So we just simply replaced A transpose as R transpose and Q transpose. Okay, and then now we see this Q transpose Q, which is like this case and this case, right? And so Q transpose Q, because the columns of Q are also normal. So that's the definition of the QR decomposition. So this guy can be just the inner product. The identity matrix. Oh, right. Yeah, thanks. Yeah. And we are obtaining this guy, right? We're obtaining this guy. So this is not a good way of proving this theorem, but let's do it this way. So R transpose R equals R transpose Q transpose B, right? So I'm just rewriting it. And then let's think about R transpose. R transpose. Okay, R transpose is, first of all, is it a square matrix or is it can it be a rectangular matrix? So suppose A was like 5 by 3, and then what is Q? The size of Q? 5 by 3, right? The same size. And then what about R? R is, so now we have like 3 orthonormal versions of the basis for column space of an A. And then what is R? R was the square matrix all the time. And then each column was working as a linear combination coefficient, right? To represent or reconstruct A1, A2, and A3, right? Okay, and so this guy is square matrix, and also it's a upper triangular matrix, and all the diagonal entries are non-zero, right? If diagonal entries is 0, and then it means that vector, that corresponding vector, is linearly dependent, right? So that's when the residual becomes exactly 0. Okay, so R or R transpose. So this guy is an upper triangular matrix, or R transpose is a lower triangular matrix. And so this guy is basically an invertible matrix. So diagonal matrix that has all non-zero diagonal entries are invertible, right? And how did we prove that? So yeah, there are several different ways, but one way was we can think about the determinant of an R or R transpose. And in the case of a triangular matrix, the product of diagonal entries are the determinant. And if we have all non-zero diagonal entries, and then the determinant will be non-zero, which means these are invertible matrices. Okay, so R is square matrix and invertible, and thus R transpose is the same. And so we have R transpose and R transpose, and then we can safely multiply R transpose inverse on the left hand side, and so we can cancel them out. Okay, so I omitted X here, and so Rx equals Q transpose B, right? And then again, R transpose is invertible, and R is also invertible. And so the solution X is R inverse and Q transpose B. Okay, so this is your least square solution. And again, this is shown as a unique solution. And why is it unique? You can think about this theorem. So again, the fact that we considered the QR decomposition of an A, okay, that means the columns of an A are linearly independent, and so the least square solution should have a unique solution. And that unique solution is defined by this. Okay, and in practice, for this guy, you don't construct R inverse. What you do is you perform or you compute the solution from this linear system without explicitly obtaining R inverse. So let me show why. Let me tell you why. So at this point, this R is upper triangular matrix, right? And then we have an X here. And Q transpose B is just a inner product between each column of Q as rows, right? And then B, right? And so we obtain this one single vector. So it's our new equation of AX equals B, right? AX equals B. And so in this case, our matrix A is upper triangular matrix. So this is an upper triangular matrix. So if you recall, or if you remember the LU factorization and how we utilize LU factorization for solving the linear system, and the LU was composed of two triangular matrices, where the first one is lower and then the second one is upper triangular matrix. And in that case, we can quite efficiently solve the linear system by just doing the back substitution or the forward substitution. So in this case, if you imagine it's equation version, and then the last one will be the first thing to compute, right? For is the solution, and then we just substitute it to the above equation, and then solve the other one, and so on. So that way we can kind of easily solve that matrix, solve that linear system. Okay, so yeah, this is a so this least square problem. So we so we now think about we can now think about three different ways. The first one is just solving A transpose A, X, and A transpose B. So we have to always solve that thing. But now let's think about the shape or the characteristic of this matrix A transpose A. So if your matrix A is just a kind of linearly independent matrix, but not orthogonal matrix, and A transpose A can be just a square matrix, but they are filled up with all non-zeros, just non-zeros. And so it's the most difficult version of the normal equation. And now the simplest case on the other hand, on the other extreme, the simplest case was the luckiest case where your matrix A has also normal columns. In that case, A transpose A is just simply computed as a identity matrix or diagonal matrix. So that is the luckiest case or the simplest case. And now, if your matrix is not orthonormal or not having an orthonormal or orthogonal columns, but somehow you obtained the orthogonalization of your columns as QR decomposition. In that case, this problem is reduced to not the simplest one, but a little bit simplest one, a little bit the simple one as upper triangular case, right? Because R is an upper triangular matrix. It's not a full matrix, so it's easier to solve, but it's more difficult than just diagonal matrix, right? So that way you can have this kind of a spectrum in terms of how difficult your normal equation is to solve. Okay. Yeah, these kind of differences are really becoming meaningful when you have to solve really large matrix. And this is quite common trick or common knowledge that you have to utilize, like in the linear regression and machine learning and deep learning and any type of this statistical learning problems. Yeah, so and I think that's it for theorem 15. Any questions? And this is the end of chapter 6. Yeah, chapter 6. Okay, then let me give you a practical. Yeah, let me give you a sense of how we can utilize this least squares in practice, like in machine learning or linear regression or statistical learning and things like that. So we are all dealing with an equation, right? Equation ax equals b, and then now by using a least square, we can solve this equation approximately even when b is not inside of our column space. So all these things are quite abstract, and they seem to be really like only the mathematical notion, which is not related to our practical real world, right? But it's actually quite closely related to our real world. So one of the easiest example of applying this least square problem in the practical machine learning problem or artificial intelligence problem is as follows. So you want to so you want to predict. So yeah, so I'm gonna give you a task of predicting a person's height using a person's weight. So I'll tell you one person is maybe 175 centimeter tall, and what is your prediction of that person's weight. Okay, that person's weight. Yeah, you can also, of course, yeah, it is not uniquely determined. So many people that have the same height may have, yeah, some guy may be fatter, or some guy may be thinner or lighter, and so on, right? But at least you collected maybe 100 people, and then you collected their height as well as weight. Okay, and then what will be your best model to predict person's weight using a person's height? So in that case, your prediction model is represented as a function. And what is a function input? Function input is weight. No. Height, right? So height. And then we want to obtain our prediction on his or her weight. Okay? And then now we want to be simple, and the linear model is one of the simplest but really powerful model. And so you can think about the linear model of your prediction as maybe A times H plus B. So for example, yeah, let's just change the role of weight and height just to, yeah. So weight was 70 kilometer, and then that person's height was maybe 170 centimeter, and 80 kilogram, and then this person's height was 178, for example. Okay, and then there may be many examples, like a 65, 160. Okay, so you have many examples like this, and then you want to train your model using all these example data. So this is a very basic and typical setting of machine learning and artificial intelligence. And so you want to construct some model, like given those data, given those examples, you want to construct maybe your model as, for example, 2 times weight plus maybe 10. So suppose this is your prediction model after observing all these examples or example pairs of weight and height. So in this case, in the case of 70 times 2 plus 10 will be 150. 80 times 2 plus 10 will be 170, right? And then let's see, 65 times 2 plus 10, 140. Is this your good model? It's not good, because it's underestimating your true height, right? It's all underestimated. So the true value was 170 and 175 and 160. Okay, so this is clearly not a good model. Then what about this? W, 2 times W, and maybe 25. Okay, and then this one will become 165, 185, 155. Okay, so this became a better model, right? Because it became closer to your target value, at least based on your training examples. Okay, and then it could be a little bit better, maybe 30, and then 170, 180, and 160. Okay, and then we are making the errors smaller and smaller, and at this point this seems to be much better than this model. But if we have like this model, and then we start to overestimate these values, right? And then this problem is exactly a least square problem. because our linear model should minimize the error between the true answer and the prediction model's output. And so let's simply construct this as a least square problem. Okay, so this is our linear model, and so let's see. Okay, then let's call this guy and this guy is, yeah, so let's think about these two coefficients as a comma b, and this will work as our x, and our matrix A part will be something like this. So 70 and 1. Okay, 70 and 1. In that case, 70 times A plus B, right? That should be what? The true answer for 170, right? And then the second one is like 80 and 1. In that case, 80 times A, 1 times B, and that should give us 178. And 65 and 1, and that should give us 160. Okay, so suddenly we are obtaining the linear system of A x equals B, but can we make them, can we obtain the exact solution? Can we make each equation to be exactly the same? It is not possible, because in this case we made two equations true, but the third equation is not true. But if we increase A or B, then it starts to make some other equations no longer be true, right? So we have to find that kind of a minimization point. Okay, so these one will give us three vector like 170 and 180 and 160, which are our prediction output. And this output should be, the difference between our output and the given output should be minimized, right? And this is exactly the least square problem. And these coefficients A and B is obtained by the normal equation, right? A transpose A inverse A transpose B, right? So this one is our A, and this one is clearly having a linearly independent columns, right? So we have this unique solution. And then this solution is your optimal coefficient A and B for your prediction model. Okay. So this is how we apply this least square problem into practical, like a prediction problem. And yeah, just for your information, this one is called a linear regression. And then you will probably learn about this linear regression maybe 2 or 3 times throughout your university life. Okay, but the solution or the algorithm to solve this linear regression is based on this least square problem. Any questions? Okay, then Then we are moving to chapter 5 about eigenvalues and eigenvector. So, yeah, this chapter is a really important part. And this is used in practice. Yeah, so much in practice. And just like a linear regression and the least squares, you will probably see this eigenvalue and eigenvector and eigendecomposition a few times during your college life. And this one is built on top of all the knowledge that we learned in the previous chapters. Okay. Okay. So yeah, I put some weird or strange cartoon here. Has anyone looked at this cartoon? Okay, so this is a Korean cartoon. So yeah, let me just briefly give you like a explanation about why I put this. What? Let's see if it see link. The URL itself, I mean, I created this URL, as a tiny URL. So it's really like a geeky or nerdy like cartoon, right? So there is a king of a derivative or differentiation. So it kills everything. So you are x cubic, like x to the power of 3, and then it's just killed by like a 3 swinging of sword, right? Because it will become eventually 0, right? Yeah. Okay, so this is the first one. So I didn't expect to look at this cartoon in this class, but yeah, let's. Okay, so still there is a king of differentiation, and then integral integral kind of monster. Let's see. Oh, maybe it doesn't contain what I intended. It may be in the third series, but anyways, here the main point that I wanted to tell you was this guy. E to the power of an x. So this guy, even after you differentiate it, it will just remain intact. It will not diminish it, or it will not disappear, right? So this kind of thing is happening in the matrix world, and that is this. So here we are differentiating here in this step, but we are in our matrix world, we are multiplying the matrix A. And then what do we multiply this matrix with? A vector, some vector, V. Okay? And then this one will become A, V, and so we keep doing that. We're differentiating over and over. And then here in this matrix world, we are multiplying the matrix A over and over. Right? A squared times x and so on, right? And here, multiplying the matrix A is really painful job. It's painful job. Even though it's easier than to solve the linear system, but imagine your matrix A is really, really big, like 100 by 100 matrix. And then you have a vector of a 100-dimensional vector. And then you multiply this, A times V and A squared times V and so on. Right? So it's, okay. So let's think about this example. 100 by 100 and we have 100-dimensional vector. How many computations do we need? How many number of multiplications and additions and so on? So in order to compute the first one, we have to do how many multiplications? Yeah, 100 multiplication, element-wise. And then we have to do how many additions? So we have to sum all of them up. How many? We have 100 scalar values. We have to add them up. And then in terms of a pairwise addition, we have to do 99 addition, right? 99 addition. By just assuming that, we only add the two scalar values at a time, right? So 99 additions, right? And then we have to do it. 100 times because we are 100 rows. So it's like 100 times 100 times 99. So you added that, and then when multiplying A again, A like a second time, and then we do this many number of So this should be like this. It should be addition, right? Yeah. So we have to do this many number of multiplication and addition, right? So this is a really large number of computation. And what if I give you some cheat key or some secret, some secret? Your vector x or your vector v is some special vector, so that a times v is just 3 times v. So this is the key equation. So that means suppose you have a vector v and then you have some matrix A, and then after multiplying A with this vector, and then the resulting vector will have different direction and different lengths, right? But if your vector v is some special vector, so that when matrix A was multiplied, then the vector direction is not changed. So the vector direction is still along the original vector, okay? And then only the length of this vector has changed by 3 times, for example, okay? Okay, and then 3 times v. And then how many multiplications and additions and so on? How many multiplications do we have to do? Huh? A to the power of something? So let's forget about this part, because so this guy is like the bad case, like just multiplying as it is. But 3 times v is like, so we have 3 and we have vector v. So let's think about how many multiplications and additions and so on should we do. So we have 100 numbers. It's quite simple. We just multiply 100 times, right? Just 100 times. That's it. So it was like 100 squared, or actually 2 times 100 squared, just approximately. Because if we consider 99 as 100, and then 2 times 100 times 100, so 2 times 100 squared, right? And so this many number versus just 100 multiplication, which is much more efficient thing. And this guy. And then let's suppose we multiply a again for the second time. In that case, we will only need, so that vector was 1, 2, 3. Maybe 1, 2, minus 1. And then we multiply 3 here. So, and then it will be 3, 6, minus 3. And then we multiply a here again. And then it will be changed by just multiplying this scalar. And then it will be like 9, like 18, and minus 9. Right? So that way, this multiplication with the matrix A, which is really complicated process, that process is dramatically reduced to much simpler computations. So this is the beauty of eigen decomposition or eigenvalue and eigenvectors. And so if you learn or study about the computer graphics, and if you are playing some video games or mobile games where the game involves like a really nice and beautiful 3D effect, like this kind of swinging a sword, and then the camera angle is rotating really nicely and dynamically, okay? And then like you run it in some virtual world, and then the sky is really nice, and then we have a shadow, and then the water is flowing, and so on. So all these are 3D things. 3D things are based on this eigenvector and eigenvalue, because you just moved one step ahead, and then all the remaining background and all the other things should be moved towards back. And then what about the rotation? We rotate it, and then all the things in the 3D world should be rotated in the opposite angle. And in that case, the rotation is just matrix multiplication operation. And you guys know how to rotate a point, right? Cosine, sine, cosine, and minus here, minus on the upper right, right? And rotating something in 3D space is exactly the same. So they are not much different. They are just matrix multiplication on some point, which is represented as a vector in the 3-dimensional. That will be the case when you do this painful process. Right? Yeah, a lot of multiplication and so on. So it will not be possible to show really dynamically in real time for your like a fast-paced gaming, right? But your matrix A, and then given your rotation matrix, and then if you found some vector V that is some special vector that this V times A is just 3 times V. Okay? In that case, if you found that vector, and then you can just efficiently do the multiplication on that matrix. So the trick is like this. So, and then yeah, this equation may be only true for some special vector, right? Special vector, right? But you can represent one vector as a linear combination of your special vectors, and that special vector each. So suppose you have this vector, and then you have maybe 3 special vectors that will form some kind of basis for your entire subspace. And then you can represent as a linear combination of these 3 special vectors using for any vector, right? And then this decomposition, I mean decomposition in terms of these 3 vectors, okay? If you multiply matrix A, and then you will multiply A with each of your special vectors, right? That will be the same as multiplying this matrix with your original vector. So in that case, each of the multiplication is just reduced to this simple operation. So that's how you accelerate and compute efficiently this matrix and vector multiplication using this eigenvalue and eigenvector. Okay, so this is not shown in your book, but it's really important, and this one will give you the actual reason about why you should study this chapter part. Okay. Okay, so that's it for today, and then let's see you next time.
If some k vectors in space Rn are orthogonal, only if they are orthogonal. B 햇을 구하는 문제네요, 결국.
그렇죠. 예. B 햇을 구하고 B 햇의 리니어 컨비네이션 코에피션트를 구하는 게 저기 리스퀘어 문제의 가장 핵심이에요.
이거네요. even 요거라 하더라도 요거면 요거다.
네, 그렇죠. B가 그래요. 이 스팬에 없으면 B랑 orthogonal projection으로 불리는 이 B 햇이 같지 않게 돼요.
네.
그죠? 그러면 같지 않더라도 우리는 이 B 햇을 구해서 즉 이 컬럼 스페이스 오브 A에 있는
그럼 B 햇도 미지 문자잖아요, 여기서.
B 햇이 미지 문자인데 B 햇은 언제나 AX로 나타낼 수 있어요. 그러니까 B 햇은 이제 뭔진 모르지만 일단 A의 컬럼 스페이스 오브 A에 있는 A인 거예요.
그럼 여기는 B 햇이 들어가야 안 들어가요?
여긴 B 햇이 들어가야 돼요.
오른쪽이요. 왕에.
오른쪽? 이건 안 들어가요, 이건.
근데 여기 B에 다 B 햇이 되면요, 이렇게 되잖아요.
가만있어. 이건 B 햇은 아닌데 이거는 그냥 B예요. 여기는. 네.
그러면 이게 원래 B하고 다르다는 걸 어떻게 증명하죠?
네?
요게 원래 요게 B하고 다르다는 거.
자, 이거는 보세요. 이게
A는 똑같은 A인데.
이게 이제 어쨌건 리니어 컨비네이션 오브 A 컬럼의 A죠.
네.
맞죠?
네.
리니어 컨비네이션이요. 맞죠?
네. 네.
근데 원래 갖고 있던 B가 애초에 그 바깥에 있어요. 그 컬럼 스페이스의 바깥에 있어요.
네.
그러면 이거랑 같지 않겠죠. 왜냐하면 이거는 어쨌건 컬럼 스페이스 그러니까 컬럼들의 리니어 컨비네이션으로 나타내진 것이고
네.
네. 우리의 B는 컬럼 스페이스로 나타내질 수조차 없는 애니까 바깥쪽에 있는 애니까.
요거 때문에 이렇게 된다는 거네. 요놈 때문에. 요놈 때문에 그렇게 달라진다는 거네. 원인이. 요 내적값 때문에 각각 그 값이 안 맞아가지고.
뭐
그러니까
그렇게도 볼 수 있고 네. 기본적으로 이거는 그러니까 A가 갖고 있는 컬럼들의 리니어 컨비네이션인 거예요.
네.
맞죠?
네, 왼쪽 거는요.
그렇죠. 근데 우리가 갖고 있는 B는 애초에 이렇게 나타내질 수조차 없었다는 거예요. B가 그러니까 span of V1 through VK에 없다면
그러면 여기서 식 세울 때 B는 그냥 B인데
네.
바깥에 B인데
네.
막상 AX는 B라고 다시 이렇게 해보면요.
네.
BH이 나오고
BH이 나오는 거예요.
다르다는 거니까
그렇죠.
뭐 쓰는 뜻인 것 같기도 하고.
아니죠. 이거를 계산해서 이 BS를 그러니까 요 노멀 이퀘이션에서 솔루션을 가지고 이렇게 AX를 만들어 보면 그래서 거기서 나온 B 햇이 있다면
오차라는 것도 인정을 하는 거죠.
네, 오차라는 거죠. 그 오차를 최소화하고자 하는 게 이 리스퀘어의 혹은 이 리스퀘어 솔루션의 어떤 가장 기본적인 출발이에요.
요거는 0 놔두고 요거 0 아닌 수만 다 주대각선을 역수취해주면 역이 나오니까 이렇게 해가지고 계산하면 요렇게 X가 요렇게 나오거든요. B에 대한 X가.
그렇죠. 네.
여기서 A는 스퀘어인지 아닌지에 대한 보장은 없고.
네, 그러나 A 트랜스포즈 A는 스퀘어예요.
그거 확실하고.
네.
그리고 요거는 조건이 그리고 이거가 할 수 있는 조건은 요 A의 컬럼이 전부 올소고널일 때만 보장이 되더라고요. 올소고널이 아니면 그것도 안 되더라고요. 그것도
네.
안 돼요. 계산이 더 꼬여요. 이렇게
네.
되면. 그때는 아예 이거 당연히 요게 되긴 되는데 경우에 따라 배수가 나오는 경우가 있더라고요. 방향이 갖고 배수 관계.
네.
요런 거. 예를 들어 그 3차원 공간에서 요 세 개 벡터로 이루어진 서브스페이스 얼 전체가 되겠죠.
네.
근데 막상 해보면 B가 막상 하면요.
네.
B 햇이 2분의 3 B가 돼버려요.
네.
그것도 그런 경우가
네.
근데
네.
일반적인 경우인가요? 근데
네.
그게?
일단은요, 내가 오늘 숙제를 좀 내줄 거예요.
네.
그래서 거기에서 아니면 혼자 A가 그냥 올소고널 컬럼이 아닌 그냥 일반적인 A를 만들었을 때, 그 다음에
요런 거 만들어줬어. 올소고널은 아닌
아닌 거를 만들어서 한번 해보고, 그 다음엔 A가 올소고널 컬럼일 때와 그
그래서
다음에
노멀이면 얘기가 어떻게 돼요?
올소 노멀일 때는 A 트랜스포즈 A가 아이덴티티 매트릭스가 되니까
그럼 그때
가장 쉬워져요. 결국은 풀어야 되는 거는 다 이 세 가지 모든 경우에서 다 똑같이 A 트랜스포즈 A 곱하기 X